map superalgebras.
Thank you for the introduction. And first of all, I want to thank Slava for the invitation. And yeah, this is basically the joint work with Lucas and Slava. And yes, so there is a natural way to construct infinite dimensional Lie algebras from finite dimensional ones. So you take G as being a finite dimensional Lie algebra, and a commutative algebra, and then you define a Lie algebra structure on the tensor product L of G and A using this bracket here. This algebra has many names in the literature. You can find, like, some people call it current algebras or generalized current algebras or map algebra. And this is actually the name that we're going to call it in this talk. Of course, you can suppose that G is a Lie superalgebra and define this tensor product here, and then work on this new Lie superalgebra and see how the representation theory works. In this talk, I'm going to suppose that G is a finite dimensional simple basic classical Lie superalgebra. This means that G is a Lie superalgebra simple, and the odd part of G is a completely reducible module over its even part, and it has this kind of bilinear form, this invariant bilinear form that is pretty similar to the Killing form in the case of Lie algebras. In this talk, so after giving you a few definitions, we'll talk a little bit about the weight Harish-Chandra modules over map superalgebras. Then we're going to see how this translates to the affine superalgebras, and finally we'll consider the affine Katsumori superalgebra as well. So let's start with our definitions here. So K is going to be our ground field. It's an uncountable algebraically closed field of characteristic 0. G is a finite dimensional simple basic classical Lie superalgebra. H, it's a Cartan superalgebra of G. A commutative, associative, unital, and finitely generated K algebra. And yeah, so we consider L as being the tensor product of G and A, and we will call it map superalgebra. So since A is unital, so it has unity, you can see G, therefore 8, as being a subalgebra of L. So we can consider L modules that the action of 8 is diagonalizable. This means that we can consider weight modules over L. And this is actually the kind of module that we're going to talk about here. So an L module V is a Harish-Chandra module if it is a weight module. And the weight spaces, they all have finite dimension. And we will call it bounded if it is a Harish-Chandra module, but the dimension of all weight spaces are uniformly bounded. OK, so this is the things that are the elements that we're going to talk about, and we can go to the results. OK, so for map superalgebras, our first goal was to classify all simple Harish-Chandra L modules in terms of G modules and parabolic induced modules. In the case that G is a Lie algebra, this was done by Brittain, Limit, and Lau, but there are other papers in this subject as well. And in the case that G is a basic classical Lie superalgebra, but the module is finite dimension, then this work was done by Savage in 2014. But we wanted to go further and consider the infinite dimensional case as well. And the result that we got was the following. So a simple Harish-Chandra L module is either a cuspidal bounded module or a parabolic induced from a simple cuspidal bounded module over a certain subalgebra of L. The thing is that L admits cuspidal modules if and only if G admits cuspidal modules. In this case, where G admits cuspidal modules, we have that the even part of G is a semi-simple Lie algebra. And with this assumption, we prove that any simple cuspidal bounded L module is an evaluation module. Evaluation modules are L modules defined in the tensor product of G modules using maximal ideals of A, or distinct maximal ideals of A. So this was what we got for map superalgebras, and you actually can, so we can think what happens when you suppose that A is the Luhmann polynomials. And when you, and this superalgebra has a different name. Some people call it loop superalgebra. So A here is Luhmann polynomials in one variable. And this algebra has this central extension by this C element here, where the bracket now is given by this formula here. So, of course, you can consider weight modules over affine superalgebras, so Harishchandra modules as well, and bounded modules as well. But now we want that the action of C is also diagonalizable. So if you take any simple module over the loop superalgebra, then this is a simple module over the affine superalgebra if you suppose that C is, the action of C is trivial. The thing is that in this case, if V is a simple module over the affine superalgebra, then V is a simple module over the loop superalgebra, that is, the action of C is trivial. So you don't get anything new when you're talking about Harishchandra modules here. But at least all the results that we got in the previous paper can be translated to the affine superalgebras as well. So we can now consider the affine Kac-Moody-Lie superalgebras. And this one is, you start with the affine algebra, and then you take this extension by this degree element D. D commutes with the central element C, but now when you take this tensor here, then we have this formula here, right? So of course, now you can consider weight modules over these Lie superalgebra as well, but now you want the action of C is also diagonalizable. In this case, we have, so we can define weight modules and Harishchandra modules and bounded modules as well. So if you take any weight module over the loop superalgebra, then you can define this LV, which is this tensor product of V and Luhmann polynomials, and define an action of G hat, which is the affine Kac-Moody-Lie superalgebra, by these formulas here. So, and actually it's not that hard to prove that V is a Harishchandra module over, so if V is a Harishchandra module over the loop superalgebra, if and only if LV is a Harishchandra module over the G hat module, over G hat. And the same goes for bounded. So V is bounded if and only if LV is bounded. So we have this assignment that sends Harishchandra modules to LG modules, Harishchandra LG modules to Harishchandra G hat modules. And the result that we got was not quite this one, but this is actually a simplified version of it. So the thing here, so you start with an evaluation module. And you can, and this evaluation module is done like this. So V0 here is just is a simple weight G module. And this F lambda is the simple highest weight module corresponding to lambda. Then this tensor product is an LG module. If you take these two scholars here. And then, so we have this evaluation module. So you can study now L of this LG module and see if it's simple or it's not. So it is not always simple, but we have this nice result here that is the following. So if there is a weight of V0 for which this map key here satisfies this condition, so image of K is this Luhmann polynomials in the variable T to the R, then we have this isomorphism of G-hat modules given by this, whereas each of these Li is a simple G-hat module. If you're familiar with the case of Lie algebras, maybe you know that these are exactly the simple modules that appear in the unpublished work of Dimitrov and Gracharov. So, but we are working with Lie superalgebras, and actually G is actually a basic classical Lie superalgebra, so it has this order grading, this Z grading, and it actually divides it in two types. The type 1 has this kind of grading here. So G is equal to G minus 1, G0, and G1. And another kind of weight modules or Hardy-Schindler modules that we considered was this one here. So you start with a G0 hat module, S, and then you define the CAS module associated to S to be this induced module here, where the action of G1 hat on S is 0. Similar to the Wehrmann modules and other induced modules that appear in the wild, this KS admits a unique simple quotient. So we have this functor called Katz induction functor that sends G0 hat modules to G hat modules. And what it does with bounded modules, at least, is this following theorem. And this one is actually the last theorem of this talk. So if G is a basic classical Lie superalgebra of type 1, then the Katz induction functor gives a bijection, actually. This map is actually a bijection when you restrict it to the sets of isomorphism classes of simple bounded Hardy-Schindler G hat modules and simple bounded Hardy-Schindler G0 hat modules. So, yeah, this was what I wanted to talk today, and thank you.
Questions? Okay, so there's no question. Thanks, speaker again. We have some time to